So we're going to take a look at how to read a potential energy and position graph and talk about both, how we would generate one and also how, if we're given a graph, how we can figure out what's going on. A copy of the PDF, there's a 14-page PDF I'm going to be using for this presentation, and this is also available on our course website if you want a copy of just the presentation to sort of leaf through on your own. So this is going to be the potential energy and position curve for a mass spring system that is oscillating back and forth from left to right. And so we can sort of see the mass spring system on the outside, and I'll talk about how to interpret what's going on there. And then the graph is in the middle here. And so what we want to figure out is how do we interpret this graph? How would we generate the graph based on what our system is doing? Or if we were given the graph, how would we use the graph to figure out what's going on? And so to do that, we're going to talk about what this mass spring system might do if we start off at position -2. So if we take and push our mass back to position -2 and then release it, what's it going to do? And so we're going to talk through how this works in terms of the spring, just using Hooke's law and what we know about forces and stuff like that to figure out what's going to happen. And then we'll talk about how that matches the energy graph and then how we could potentially work backwards as well. But the idea is going to be, if we start at position -2, what's going to happen? How would we generate the graph, or how would we interpret the graph for that situation? So I'm going to go through, there's going to be a whole series of things we're going to look through, and each time we cycle through, we're going to cycle through this a few times looking at different things each time. And so this very, very first time, you can just ignore everything that's in the middle. We're going to get to that later. Don't read it now because it's just going to cause extra confusion. For now, we're just going to pay attention to going around the outside, and specifically the one that is circled. So we said we wanted to start at position -2. And so if we had a mass spring system, the way we would do that is we would have to retract the mass back to position -2. So we've got equilibrium marked here. And so we can see we've displaced ourselves 2 squares to the left, so -2. And we're going to release it from rest. So our velocity is 0. And we know the spring is going to try to push itself back to equilibrium. So the spring is going to be pushing to the right. And so if we have something at rest and a force pushing it to the right, it of course is going to move to the right. And so that's what we see in our next picture. The spring starts pushing the block to the right. And so now the object is moving to the right. But the spring is still compressed. It's not back to equilibrium. And so it's still going to be pushing it to the right, and so we are going to expect it to continue moving and actually getting faster because it's still being pushed to the right. And so here we see the velocity is larger than it was before. So here we had a small velocity, here we had a large velocity because it's continued to get faster and faster and faster as the spring has been pushing it. We're finally back at equilibrium. So we're back at the dotted line where we started. This is where we know the spring force is going to be 0 when we're back at position 0. Of course, although there's no force pushing on the block, it does still have inertia. It was moving to the right rather quickly, and so it's going to keep moving to the right, even though the spring's not pushing it to the right anymore. Of course, as it goes to the right, that stretches the spring out, and the spring starts to pull back to the left. And so now as the object moves to the right, the spring starts to pull back on it, which slows it down. And so we see our velocity here is smaller than it was over here, but it's still moving to the right. It's just slowing down as the spring stretches out and pulls backwards on it. Of course, eventually, the spring has been pulling backwards hard enough and for long enough that it's able to stop the object. And so it gets to some maximum position over on the right side, at which point its velocity goes to 0. And so it's at rest with its largest displacement to the right. And now, since the spring has been stretched out this way, it wants to go back to equilibrium. And so the spring continues to pull to the left, which now allows the object to actually start moving to the left. And so then it just sort of repeats itself in the opposite direction. We start moving to the left with a little bit of velocity at first, and as we continue pulling it to the left, as it moves to the left, it's going to get faster. And so when we get back to equilibrium, it's moving quite quickly to the left. We're at equilibrium, so the spring's not exerting a force anymore. but the inertia of the object still causes it to move to the left. And as it goes to the left, the spring starts to compress, and so it starts to push back to the right. And so now as we have a velocity to the left and a force to the right, it's going to start to slow down. So we see our velocity getting smaller than it was here. And then eventually, as the spring continues to push to the right, eventually it stops the object, and so the object is going to reach some maximum compression on the left side, which you'll notice is back to our initial position. And then the cycle just keeps repeating, and the spring oscillates back and forth, back and forth, back and forth. Okay, so that's just what's going on purely in terms of Hooke's law and what we know about forces and Newton's laws and stuff like that. Let's think about it in terms of energy. So in terms of energy, we start at rest, and the spring is compressed. And so it has a bunch of elastic or spring potential energy. And since it has a bunch of potential energy and it's pushing the object to the right, the object is going to start to move to the right. Of course, as it starts to move to the right, the spring starts to decompress. And we know the closer the spring is to equilibrium, the less elastic potential energy or spring potential energy it's going to have. But the total energy has to be constant. This is an isolated system where we're going to have conservation of mechanical energy. And so if there's less potential energy in the spring, that means the kinetic energy of the system has to go up, since there's no other kinds of potential energy we're going to be gaining. And so if we lose potential energy, we gain kinetic energy, which means that we gain some speed. When we get to the middle, this is where there is no energy stored in the spring. When we're at equilibrium, the elastic potential or spring potential energy is zero, which means all of the energy is kinetic, and so we're going to be going the fastest here, which is why we see the highest speed. But then as the spring continues to move to the right, now it starts to stretch out, so we have some potential energy now, which means we have to be losing kinetic energy, so our speed gets lower. And then as the spring stretches out even more, the potential energy gets even higher until eventually all of the energy is potential energy. There's no energy left to be kinetic energy. And if there's no kinetic energy, the object is going to be stopped. So our velocity is zero. And then it repeats on the way back. So on the way back, we wind up when it's stretched out a little bit. It's got a little potential energy, but that also means it can have a little kinetic energy because the energy is going to be split between the two. When it gets back to equilibrium position, as it's moving to the left, all of the energy has to be kinetic energy because there's no potential energy stored inside the spring when it's at equilibrium position. So it's going to be moving the fastest. So we see the largest velocity arrow. And then as the spring starts to compress, it's got some energy stored inside of it, so it loses some kinetic energy so it can gain that potential energy. And then once the spring is compressed enough, all of the energy is back to potential, which means the object stops. And so we're just looking at something that is switching back and forth between potential and kinetic energy. So we can see that on our graph then. So this graph, ignore all the words for now. Just look at the circled dot. The circled dot is going to correspond to the picture. We said here at the beginning, this is where it had the maximum potential energy because the spring is compressed the most, and so we can see our potential energy is a relatively high value. When the spring is less compressed, it has less potential energy, so we have a smaller potential energy. We said this is where the potential energy is zero, and so we can see our potential energy value is zero, it's the lowest. Then as the spring starts to stretch out, it starts to store some potential energy again, and so we see it gaining a little bit of potential energy. And then when the spring is all the way stretched out, that's where it has the maximum potential energy again, the same potential energy it had on the other side. And so because 100% of the energy is potential in both cases. And so we get a high potential energy value here that is the same as the potential energy value we had when we were all the way on the left, because in both cases, it's got no kinetic energy, all potential energy. And then as it goes back, we've got a little bit of potential energy because we're a little bit stretched out, so we got a little potential energy. And then we got a no potential energy, little potential energy, and then a lot of potential energy. Now, you'll notice these dots correspond not only to the potential energy, but also to the position. And so here we're at position -2, so that's why it's this dot. Here we're at position -1, so the block is only 1 to the left of our lines, so we're at position -1. Here we're at equilibrium, position 0. That's why the dot goes at this point on the graph, because you can see our block, our position is 0. It's at equilibrium. And then as it moves to the right, its position is 1, which is here. And then the furthest it'll get to the right is 2, which is right here. And then it just goes back 1, 0, -1, 2. And so we can understand where these values are coming from just based on how the system works. And we have a potential energy that is defined at any point based on the position of the system. And so we can make a graph that defines what its potential energy is based on what position the system is. Because if we know what position we are in, that defines how much the spring is stretched or compressed, which is what defines how much potential energy it has stored inside of it. All right, now the next thing we need to talk about then is how do we go backwards? So it should hopefully make sense why the system does this in terms of forces and motion, and why the graph would have to look like this. But what if instead of being given the system and asked to generate the graph, we were given the graph and asked to figure out what the system is doing? How would we work backwards? And so that's the next thing we need to do, and that'll be in the next video.